Hi everybody, this is the video where I do the homework for section 4.3, multiplication rules for probability. And you can see that or at least my computer screen is in homework mode. I have Hawks here, I have my calculator in the middle, and I have OneNote in draw mode over here. And in Certify, what you gotta do is get 6 of 9 questions correct, and you will have certified. As long as you do that before the homework, you will earn the grade of 100. If you don't, you'll earn a lesser grade once you eventually get it done. As always, I'm going to go into practice. Why? Because if I run into a mistake, it will help me find the correct answer, and Certify, it will just tell you that you're wrong. So if you get stuck, come back here and practice. Okay, and this is the first of 9 problems. The first one is, determine if the following events are independent. Not shutting off water in the kitchen sink and receiving a high water bill. They seem dependent to me. If the water run, the water bill is going to be high, especially if you're in California where water happens to be precious. So this is dependent. Okay, next one is the exact same type of problem. Determine if the following events are independent. Jeff runs out of gas on his way to work, and Rebecca wins the state lottery. Now, there might be some kind of crazy, contrived reason why they would be dependent. Like maybe Rebecca and Jeff are married, and since she won the state lottery, she decided not to go to work, and so Jeff borrowed Rebecca's car, not knowing it was out of gas. But chances that seems a little absurd. I think these events are independent. Jeff running out of the car really should have nothing to do with Rebecca winning the state lottery, unless they are related in some crazy way. And that's what we're going for. This is a question relative to the fundamental counting principle. You are using a local home remodeling company to remodel your kitchen. You have 13 different cabinet door styles, 14 countertop styles, and 15 different types of flooring. So this is basically a multi-stage experiment. The question here is, how many different kitchen remodels could be done using these choices? In other words, what is the size of the sample space? Do this over here. So remember, the fundamental counting principle tells us that the size of the sample space is going to be equal to the outcomes associated with the first stage, 13, times the outcomes associated with the second stage, 14, times the outcomes associated with the third stage, 15. 13 times 14 times 15 is 2,730. That's what we want to put in here. And there you go. Okay, next, a coin is tossed 9 times. How many different outcomes are possible? Exact same type of problem. We are looking for the sample space. And that is going to be 2 times 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 2. 1, 2, 3, 4, 5, 6, 7, 8, 9. 2 per stage. That, of course, is 2 to the 9th, which should be 512. Okay. Next, we have another fundamental counting principle problem. And once again, we're looking for the size of the sample space. So here we have a value meal package at Ron Subs. I guess you can figure out where I got the example from. Consists of a drink, a sandwich, and a bag of chips. There are 6 different types of drinks at stage 1, times 4 different types of sandwiches, that's stage 2, times 2 different types of chips, that's stage 3. As a matter of fact, this one's identical to the example. How many different combinations are there? Well, 6 times 4, which is 24, times 2, which is 48. 48. On to 6. Okay, now we're getting some interesting stuff. Suppose that you keep a jar of change on your desk. Currently, the jar contains 18 pennies, 15 dimes, 17 nickels, and 7 quarters. What is the probability that you reach into a jar and randomly grab a penny and then without replacement grab a nickel. So we want to find the probability of grabbing a penny and then grabbing a nickel. That's going to be equal to the probability of grabbing a penny. And remember, since it's without replacement, this is conditional probability. So the probability of grabbing a penny times the probability of grabbing a nickel, given that you already grabbed a penny. Okay, well, the probability of grabbing a penny, that should be pretty straightforward. That's going to be equal to the number of pennies divided by the total number of elements in our sample space. Number of pennies happens to be 18. The number of elements in our sample space, T, happens to be 18 plus 15 plus 17 plus 7. And that gives us 57. Okay, so the probability of drawing a penny is going to be 18/57. Okay, now the probability of drawing a nickel, given that a penny has already been drawn, that is going to be equal to the number of nickels that we have divided by not the sample space, because remember we took a penny, so it's going to be equal to divided by the sample space minus 1. That is going to be 17 divided by 56, 17/56. So then the probability of drawing a penny and then a nickel is going to be the probability of drawing a penny, 18/57, times the probability of drawing a nickel, given that you already drew a penny, 17/56. Okay, now to do that on a calculator, we can do 18. Oh, I have to go on the calculator first. There we go. We can do 18 times 17. That's my numerator. And my denominator is going to be 57 times 56. Now I can just basically highlight my numerator. All right, hit enter. Divided by, highlight the denominator. Hit enter. And that is my answer. I can either write down 0.0959. Notice that this is my fourth decimal place. That's 5 or higher. I need to round up. Or I can see what the reduced fraction is by hitting math and then hitting enter twice. Enter, enter. Or I can write down 51/532. This is actually the reduced fraction. Either way will work. Let's go ahead and try the fraction here, or the decimal, 0.0959. And there you go. And we have 3 more problems left. 2 cards are drawn without replacement from a standard deck of 52 cards. What is the probability of choosing a dime or a diamond, and then without replacement choosing a black card? Okay, so we want to find the probability of choosing a diamond. I'm just going to call that D, and then choosing a black card. That will be equal to the probability of choosing a diamond times the probability of choosing a black card, given that you already chose a diamond. Okay, now if you're confused about this, it's always good to click on here and take a look at our deck of cards. We always have 52 cards, so T will be 52. So the probability of choosing a diamond is going to be equal to the number of diamonds that we have divided by T, which is 52. Notice that we have 13 diamonds, so this is going to be equal to 13/52, which of course is 1/4. Okay, now the probability of choosing a black card, given that you already chose a diamond, is going to be equal to the number of black cards that we have divided by, well, not 52, because remember we chose a diamond, so it's going to be T minus 1. Now, how many black cards do we have? Well, we have 13 here. We have 13 here. 13 spades, 13 clubs. We have 26 black cards. And now instead of 52, because remember we already chose a card, we only have 51. So the probability of choosing a diamond and then a black card is going to be equal to 1/4 times 26 divided by 51. Okay, so in the numerator we have 20. Let me get over here. In the numerator we have 26. In the denominator we have 4 times 51. Okay, highlight the numerator, hit enter, divide, highlight the denominator, hit enter twice, and that is our answer. If you want to know what the reduced fraction is, we can hit math and then hit enter twice, and that is our reduced fraction. So we can either put in 0.1275, we would need to round up because that's 5 or higher, or 13 over 102. I'm going to put in the fractions, so I'm going to click here, get rid of this. I'm going to hit slash, and this is the type of fraction where you actually have to use tab. So it's going to be 13 tab 102. Okay, 2 more problems left. Now these 2 you need to be careful about and understand what they're asking for. So here we have a box that contains 17 green marbles and 8 white marbles. If the first white marble chosen was white, what is the probability of choosing without replacement a green marble? Okay, so they're telling you the first marble is already white. They're not asking for the probability. That already happened. So this is a conditional probability problem. They want you to determine the probability of choosing a green marble given that you already chose a white marble. Okay, well that is going to be equal to the total number of green marbles that are there divided by all the marbles that are left after you've chosen a white one. That is going to be t minus 1. Okay, t happens to be equal to 17 plus 8, which is 25. So t minus 1 is obviously 24. How many green marbles do we have? We have 17. T minus 1 is 24. That is our answer. Now, you can write, this actually is a reduced fraction. How do I know that? Well, because I know 17 is a prime number. The only factors of 17 are 1 and 7, and 24 is not a factor of 17, so I'm pretty good there. So we can either write that in, or if you wanted to, you could write in 0.7083. I'm going to just go ahead and do the fraction part. That way you guys can see it a little more often. So this is going to be 17. I just hit the slash button. I hit the slash key. 17 tab 24, and there you go. And that brings us to our last problem, which is exactly the same type of problem. 2 cards are drawn without replacement from a standard deck of 52 playing cards. What is the probability of choosing the heart for a second card if the first card drawn without replacement was a club? So they're telling you the first card was a club, and given that, what is the probability of choosing a heart? So once again, they are looking for the probability of choosing a heart given that you already chose a club. Okay, that is going to be equal to the number of hearts divided by the number of cards that are left after you've chose a club. That will be t minus 1. Of course, in this case, t is equal to 52. And let's take a look at what's going on here. Here's our standard deck of playing cards. Okay, remember we chose a club, so 1's down, which is why we have 51 left. So this is going to be equal to 51 in the denominator. How many hearts do we have? Well, come down here. We have 13. Okay, so we have 13 hearts. And that right there is our answer. As a decimal, that would be 13 divided by 51, which would be 0.2549. Fifth decimal place is a 0, so that's all we need. And let's go ahead and put this in as a decimal. 0.2549. And there you go. And that is how you do your homework. Although you can only need to do 6 of the 9 problems to get 100 on this homework before the due date, I would encourage you to do all 9. Don't skip the last 3, because you will see one of those problems on your test. So you want to practice it a couple of times to make sure you know how to do it. And that is everything relative to section 4.3. Once again, if you have any questions, please feel free to contact me. This is Bob Boyle, signing off.